Hello everyone and welcome back to another video. The stock markets might be collapsing tomorrow. People think we are in the great AI bubble. So there's a high risk that we could lose everything if we invest in the wrong stocks. How does that relate to quantum computing and how quantum computers might help in the future to mitigate those risks, bubbles bursting in the financial markets is a topic of today's video, as we are looking into JoS Quantum, JoS Quantum, a company that is active in the consulting space, but also helping to build simulations and build algorithms for quantum computers. Their main focus, or one of their focuses, is on financial applications and let's say insurances related to that. We are going to learn more about all of this, and there will also be nice interactive elements even in today's video. So if you are interested in how all of these things work together, or you want to learn more about JoS Quantum, a German company in the quantum consulting space, then stay tuned for today's video as we are diving deeper into JoS Quantum. And with that, as per usual, we start here on their website, JoS Quantum, algorithms made in Germany. It says a simulation of complex systems using quantum computers. Our core expertise is developing quantum algorithms for real industrial use cases and the engineering judgment to tell you what they will and won't require from quantum hardware. So here's a little overview about the services that they are providing. It says training and education, use case development, hardware requirement estimation. We will see an example of that also later on. IP development, technical due diligence, and then of course they are also open to talk about other things, and there's an email here to reach out to them. There are interactive demos, we will look at those later on, and some links to research papers that they've been contributing in, ranging from 2021 or as early as 2021 all the way to 2026. I'm recording this video in July of 2026, so you can see this is very much still active here with the Pauli cloners for Pauli channels, presents a quantum circuit architecture for 1-to-2 cloning of n qubit registers, extending the new Griffiths architecture, explores the relationship between Pauli errors, mutually unbiased bases, and Pauli cloning. Now there's also some patents mentioned here, which I think makes sense because looking back here at the services, right, IP development is part of it, use case development, so they show that okay, they have these interactive demos, right, so it's hands-on, there's research work being done, there are patents that are linked here, so this is all, let's say, creating somewhat of a trust situation, right, that they can be trusted and they know what they're talking about. Here is a list of, let's say, labels. It says you are in good company. I don't know if this is like collaborators, funders, or whatever. You see Bundesministerium für Bildung und Forschung, Bundesministerium für Wirtschaft und Klimaschutz, so the German ministries, but you also see DLR, Quantum Computing Initiative, NVIDIA Inception Program, and many others. Deutsche Bundesbank, so the German central bank, mentioned here as well. Now, looking at the services in a little bit more detail, it says quantum at the depth you need it. So here's again the offering, right? So they're different, let's say, quantum education formats that they are offering. That's at least how I understand it. So keynote on quantum technology, half an hour to an hour, I guess. Then introduction to quantum computing, 2 hours, and 2 hours introduction to quantum communication and security. So these are, let's say, I guess, speaking engagements which you can book. There are also trainings on top of that. So you see here 1 to 5 day training and in-depth algorithm development, proof concept, 3 to 24 months, and then ongoing strategic advisory and on future priorities, as, let's say, ordered by the size of the engagement, right? Starting from hours all the way up to months or like continuous engagement. Again, link down here to the email address to reach out to them. So that's on the services side, but I mentioned before that there is some interesting demos here as well, and let's quickly take a look at the Shor demo. So let's take a step back. What is the Shor algorithm? What is this referring to? It is about the fact that most of our communication today is based on an encryption scheme called RSA. RSA is using so-called prime factorization. So if I, for example, give you the number 15 and I ask you what are the two numbers that you need to multiply to reach this number 15, there's only one, well, actually there's two answers. You could say 1 times 15. Okay, that's clear, right? That's always the case. But in the case of 15, it could also also be 3 times 5 if you're limiting to integer numbers. So there are only these two answers, and of course the second one is the more difficult one, the other one is trivial, right? Now that being said, it also means that, okay, if you have bigger numbers, it becomes more difficult to actually find those numbers. And in these cases we talk about prime factorization, right? Because there's only one right answer, because the two numbers that you're multiplying with each other, they cannot be divided into integer numbers, into integer factors again, right? So they're the smallest integer division possible, and that's what a prime number is. So 3 and 5 are small numbers, so it's still comparatively easy because you can just figure out, okay, for 15, the biggest possible divisor is 15 divided by 2, right? So 7.5. So you only need to know all the prime numbers until 7.5. So you're basically going through those, and then you can just multiply those with each other and figure out which one gives you the 15. But as these numbers get bigger, it becomes more and more complex to actually figure out the prime factorization. And that's the idea behind this encryption, that, okay, if I give you the two prime numbers, it's easy to verify. But if I only give you, let's say, the product of those numbers, the multiplication between those, it's incredibly hard to figure out, or it's exponentially hard or very difficult to figure out what are the two prime factors. And if you just do this with big enough numbers, even the biggest supercomputers will not be able to crack that easily. And that's what the RSA encryption is based on. Now you can also do some estimates, so you can estimate the complexity of those algorithms, as in like how many steps, how does the number of steps that a computer needs to run grow as a function of the size of your prime numbers, right? And then you can say, okay, if I just take big enough numbers, it takes longer than the existence time of the universe, or what we think is the existence time of the universe, to actually break this, and that's what we consider them to be safe. Now with quantum computers, this whole paradigm shifts, and that's where the Shor part comes in, because Peter Shor invented in I think in the 90s sometime, here it also says 1994, he invented an algorithm that could run on a quantum computer. Back then there were no quantum computers, not even very simple ones, I think. He invented this algorithm, which is now called the Shor algorithm, which shows that, okay, with a quantum computer we can solve this prime factorization problem much faster. And that's by using interference pattern and superposition between those qubits to actually run the algorithm and kind of probe all of the numbers at the same time. In fact, what you're doing is you're looking at the interference pattern, and then at some point running this quantum Fourier transformation, you can basically see that the interference pattern in specific qubits that correlate to the prime numbers will be very strong, and that's how you can figure out these exact prime numbers. If that was the case, so if we had a quantum computer today that could do this, then we could crack all the encryption. So that's already, let's say, dangerous. But then on the other hand, looking at today's quantum computers and what is publicly known about the status, I think we don't have to be afraid yet that this is going to happen in the next couple of days. Now, why does it still play a role? And that's where things are becoming interesting. It still plays a role because there are certain secrets that you want to keep secret for a long time. So if your doctor is sending you an MRI image of your body, like from an MRI scanner, you might not want this to be exposed to the whole internet. So when they send it to you, it's encrypted by today's encryption standards. And if somebody would be sitting in between and listening to that and kind of taking this information, storing it on a hard disk drive, then okay, maybe in your lifetime it could still happen that there's a quantum computer which could crack this, and then people could see, or somebody could see this data and then know something about your health condition. And there are also other secrets which need to remain secret for a whole lifetime. So there could be banking reasons and other stuff as well. So that's why it is important to be able to assess, given today's RSA encryption, to be able to assess how safe this actually is. And it would be great if we could basically do this by factoring in the roadmaps of the big quantum companies and, let's say, pinpointing or guesstimating a year at which this is becoming relevant. And luckily, this is exactly what they did here. So if we are scrolling down, we can see here the key size of our RSA key. So in this case, it's 2048. So you could also just paste your real public key in here that you're using, for example, to encrypt an email today. And then we just take the the size estimate, get the size from the key itself. And then you can basically choose between surface code, which is what has been proposed as an error correction scheme in the past. So quick step back, what is error correction? Today's quantum computers, with the qubits they are running and accumulating errors. And after some time, these errors, they are getting so big that you cannot effectively run those very advanced algorithms like the Shor algorithm on those machines. So you need to actively correct for that, which creates a certain overhead. And one way of doing so when correcting these errors is quite difficult, much more difficult than on classic machines. One way of doing that is the surface code. Here they take the estimate from 2019 publication. Another one that is more recently developed is this quantum LDPC, so 2026. And if you are now choosing one of those, you can basically run an estimate as to how long this message that you've just encrypted with this key, or that you're encrypting with this key, is kept secret given the timelines of today's quantum companies. And in this example, 2048 keys and the LDPC algorithm, we can see here that the projected timeline to actually break this is 2031 to 2033. If we are going to the more conservative one from 2019, it's 2039 to 2041, depending on which timelines you're looking at. Here we are looking at the roadmaps publicly available from IBM, Quantinuum, and IonQ. And here you can also see the expected qubits, physical qubits that you need to have to run this, right? So reach 20 million physical qubits, then run error correction on top of that, and then you can estimate that you end up at something like 6,000 logical qubits. And now if you're running the expected number of gates on that, it will take you 8 hours to actually crack this encryption key. If you're, let's say, moving to this LDPC scheme, it's the same story, right? You need this number of logical qubits here. The number of physical qubits is actually a bit less, so you only need 100,000. So still, in order to run this in 8 hours, we can already assume that given those roadmaps here, it might already happen in the next couple of years, so 2031 to 2033. And that's something to keep in the back of our minds as we are using today's encryption and sharing messages. That might not be extremely relevant in what you're doing in your private life, but as a corporate, these timelines here, they are already pretty relevant, especially for the bigger corporations that usually take a certain time to actually, let's say, deploy this throughout the organization. If you're talking about multinational companies, that can take a couple of years. And looking at this timeline here, 2031, I mean, I'm recording this in 2026. This is 5 years, roughly 5 years from now, right? So in the worst case for the encryption. Here you can see the data that this is based on, right? So here everything starts in 2012 here with this. I think this is, let me see, what does it say here? Algorithmic requirements. So this is the, let's say, algorithm side of things. How do the algorithms become more and more effective, more and more efficient, right? So here you see the number of qubits on this exponential scale here is going down rapidly. So in the past, they said in 2012, when I started to learn about quantum physics, that was still 1 billion qubits. By the time I was finishing my master's, or I had finished my master's already, it was only 20 million. And if we are looking at today's value, we are like somewhere around this 100K in 2026. And the projection goes that, okay, maybe there's even some more room to squeeze this to even lower values. Now, on the other hand, if we are looking at the qubits, and here we see, let's say, the main platforms that currently get the most attention, which is superconductive and ion traps. Maybe there's other technologies overtaking those in the future. But if we are looking at those two, and I mean, here we see the Sycamore, which is, for example, a Google processor. Then we also see Quantinuum. So there are different processors, different company roadmaps factored in here. Then we see that the number of qubits is going up. We are in 2026, so we are here, and the projection is that, okay, here with the scaling that they are, say, predicting, this will cross somewhere here around this 2031 point, and it will be able to run those algorithms on existing machines. So that's, let's say, the forecast. There's also some explanation down here. So fixed post-quantum cryptography, so how to kind of solve this issue. issue, as well as some honest caveats, as in like, okay, these are order of magnitude estimates. So there's of course some guesstimation coming in there. These are roadmaps, not guarantees. So that's what companies are aiming for and what they might also be used to attract investor capital, right? There's some intention behind those roadmaps to get people excited about the technology. So maybe it's longer, that's not sure. And then there are some other factors that are playing a role here. You can go through this in detail by yourself. So this is about, let's say, the encryption and the error detection. I think it's a very valuable resource here. The other one is this risk demo here, which I think is also very interesting. So that talks about, and that was the opener of today's video, right? That talks about risk estimation. So business risk estimated on a quantum computer. It talks a little bit about how risk estimation works. So here, where do we have it? Here is this risk network. So you see different sources of risk like market shock, liquidity squeeze, counterparty default. You see certain probabilities that are attached to those, and then you see these connections here, these arrows between those different risk items that are, let's say, the conditional triggers. So they are mentioned down here, and they have also probabilities attached to them. And now you can basically run a simulation through this risk network using a quantum computer, because actually this problem matches pretty well, and there's a quadratic speed up comparing a quantum computer to, let's say, a classical scheme. And that's what's said here, the result behind our 2021 work on a risk model used by Deutsche Börse Group. So this is actually like a real world application or a real world algorithm that's being used in industry that is now, let's say, being modeled in a quantum fashion here. And then, you can play around with these different parameters. You can run a simulation here with 5 qubits, with 3 qubits, and then you get the time that it takes to run the simulation. So 6 milliseconds, and then if you run it on 7 qubits, and you get, let's say, the finest simulation, then you get 45 milliseconds. And here you see the circuit that is being used to run those simulations, as well as the risk estimation down here. So in this case, you see the QAE, so the quantum estimation is 11%. If you are, for example, only running on the 3 qubits, which is a bit faster, you are reaching those 14.6%. And this here is the, let's say, proper value, like the ground truth. And you see here it's 11.8. So the second one, which has more qubits, is more accurate, of course. Then resources used are also listed down here. So this is what you would want to measure. This is like an example what you would want to measure if you're comparing a quantum algorithm with a classical one. You want to know how accurate is it, how much resources does it take. It's basically like a high level example of what you could get if you work with them or hire them as your consulting partner, right? Here's a little bit more information how it works. You can go in the details of this well. I see the formulas down here and some explanation. I will not go through the details of that, as well as the linked reference here to this 2021 Deutsche Börse Group work that was been mentioned before, and the caveats that are listed down here again for this example. Then we see risk with a Q at the end here. Let's wait for this to quickly load. Let's hope it does. Maybe I do this again. There we are. Oh, I think it just kicked me back to where I was before. Okay, so that just leads me to a login interface. I think Risk is the platform that they are offering, or the framework that they are offering. But I think we cannot see much from the outside. There's also a link up here to a GitHub repository, which I think is where all of the, let's say, coding work is happening in the open. So of course not if you are, let's say, doing a consulting work with them, but everything that they want to share is on the GitHub repository, which always indicates that there's also some technical work ongoing and not just people talking about stuff. So I think that's also very nice to have that linked, and the LinkedIn link as well. As mentioned, the company is based in Germany, in Frankfurt, which is where all the banks are. So that's probably makes sense to have this finance and let's say insurance relationship in here as well. So it makes sense for them to be based somewhere around Frankfurt in this case. That's about everything I wanted to share with you about JoS Quantum today. I hope you found it interesting. If so, please make sure to check out our YouTube channel. Also, quick shout out to our quantum education experience. So we have a course that is dedicated for decision makers trying to make their first step into the world of quantum technology, that want to understand the market. Could also be interesting for quantum founders to understand the market around them, as well as investors trying to make a first investment into the world of quantum. This course is now open for pre-registration. You can find the link down below the video, so feel free to check that out. And I'm looking forward to see you in the next video again. Until then, as always, stay hydrated. Bye bye.